Welcome back everyone. In this lecture, I will state and prove all the Sylow's theorems. Okay, so let us see the statement of Sylow's theorems. So recall first what is the Lagrange's theorem. So one can think the very first Sylow's theorem as a partial converse of Lagrange's theorem. So Lagrange's theorem states the following. Okay, for any subgroup H of G, we have order of H divides order of G. Okay. As I said before, Sylow's theorems are only for finite groups. So we assume all the groups involved in this talk are all finite groups. Okay. So to begin with, G is a finite group. So this is what Lagrange's theorem says. Okay. So now one can ask this question. So if you fix this cardinality of the group, okay, suppose if you know that the cardinality of group is n, and then if you fix a divisor d of n, okay, so d is just a divisor. So one can ask this question whether there exists a subgroup of order d in G. Okay, so this is the converse, whether there exists a subgroup of order d in G. So this is the question. So we already seen this converse is not true. Okay, so we looked at this alternating group of size A4, and then we proved that there is no subgroup of order 6 inside A4. So A4 has the cardinality of S4 divided by 2, which is 4 factorial divided by 2. So that means it's 4 into 3, which is 12. Okay, 6 divides 12, but there is no subgroup of order 6 inside A4. So the converse of Lagrange's theorem is not true. So the converse of Lagrange's theorem is not true. Okay. So then what's about some partial converse? Okay. So we already seen this Cauchy's theorem. So what Cauchy's theorem says, if you have, okay, recall, if you have a divisor P for this order of the group, okay, and P is a prime number, so then we proved that there exists a subgroup of order P. There is a subgroup of G of order P. Okay, so that is what Cauchy's theorem says. So that means some partial converse of Lagrange's theorem is true. Okay, if the divisor is prime number, then we have the converse. So now what Sylow asked, whether it can be generalized to some prime power. Okay, so first we will state this result for actually the highest prime power that is dividing the order of the group. Okay, so then we will see later for any prime power that must be true. Okay, so let me state the Sylow's theorem. So here is the first statement, I call it S1. Okay, so before that let's fix some notations. So let us say that the order of the group is exactly some p power k times m. Maybe I will use, yeah, it's fine. And then where m and p, they are relatively prime. So what is the meaning of that? P is a divisor. Okay, so we assume that this k is also greater than or equal to 1, otherwise there is nothing to say. Okay, so this k is also greater than or equal to 1. So p is the divisor of this order of G, and then p power k is the highest power of p, such that p power k divides the order of G. So that means p doesn't divide m. So p and m are relatively prime. So if this is there, so then we can state the first theorem. The first Sylow's theorem actually guarantees that there exists a subgroup H of G of order P power K. Okay. Such groups are called, such subgroups are called silo P subgroups. Okay. Such subgroup is called silo P subgroup of G. Okay. So, this is very important statement. So, now let us state the second theorem. Okay. The second actually statement of this Solo's theorem states that it compares two different silo P subgroups. So, you fix P and then look at silo P subgroup. Silo P subgroup by definition it is a subgroup of G such that order of that group is some power of prime P power K, where P power K is the highest prime power that divides order of G. So, now you take two different silo P subgroups. Okay. So, take two different groups, call it H and K. So, any two silo P subgroups, let us say H and K of G are conjugate. So, that is there exists G in G such that GH G inverse equal to K. So, note that if we take this set of all silo P subgroups, so then we are saying that the group G is acting on that set of all P silo group via the conjugation, and that action is transitive action. So, that is what the statement 2 says. Okay. And since they are all conjugate under some elements of G, so you can see that they are naturally isomorphic to each other. Okay. They are not just some subgroups. Okay. So, they are all isomorphic subgroups. So, that is what the statement 2 says. The statement 3, so this is about the number of such silo P subgroups. Okay. So, if we denote K by the number of silo P subgroups of this G, of course, up to isomorphism there is only one because all of them are conjugate. So, now we are counting it as different distinct subgroups. Okay. So, if you take the number of silo P subgroups as subgroups of G that you denoted by K, so then you can prove that. So, then we have P, this K is congruent to 1 modulo P. So, in particularly K and P they are relatively prime and K is congruent to 1 modulo P. So, we call this is Silo first theorem, second theorem and third theorem. So, they are very fundamental results for finite groups. Okay. So, one can use, like I said, one can use these results to determine groups of small order, and we will also see many interesting applications of Solo's theorem in finite abelian groups theory and so on. Okay. So, the statements are I believe very clear. Okay. You write order of G as some P power K times M, where K is the highest power of P such that P power K divides order of G, and then because of that the M and P they are relatively prime. So, in that case you have a subgroup of G of order P power K. So, that subgroup is called silo P subgroup. So, if you take two such subgroups that is having order P power K, they must be conjugate to each other. In particularly they are isomorphic to each other. But if you count the silo P subgroups as distinct subgroups of G, then that counting that will have exactly if you call it K, that will have this property, K is relatively prime with P. Not only that, K is congruent to 1 modulo P. Okay. So, these are the three statements of Solo's theorems. So, let us prove this one by one. So, the proof of S1. Okay. So, to prove this, so let us first look at some silo P subgroup. Okay. One can assume the existential and then try to see like how one can prove such statement. Okay. So, if you look at this group, okay, G. So, the G has this order p power k times m. Okay. So, the order of the group is p power k times m. So, this is just some motivation. Okay. So, motivation for the proof. So, in case you have this H, which is a subgroup of G such that the cardinality of H is p power k, then from Lagrange's theorem it is immediate that the cardinality of G modulo H is going to be exactly m. But G mod H is what? G mod H is going to be all possible left cosets of this H. Okay. So, if you take all these left cosets, they all have same cardinality as H. Okay. So, G is naturally acting on this G mod H. Okay. It is an invariant subset, but you can see that there is this bigger set, okay, on which also G acts. So, that is what we denoted by sigma k, okay, or let us call it sigma. So, what is sigma? Sigma, those subsets of G such that the cardinality of S is exactly p power k. Okay. So, I am looking at all possible subsets of G that has exactly cardinality p power k. So, we already seen G acts on sigma via this left multiplication. So, take G dot capital S to be just a GS. So, this is action that we have already defined. So, now we already seen that if H is a subgroup of G, so then the orbit of this H, okay, you under this action. So, this action that we are going to use, under this action the orbit is going to be, so those conjugates like left cosets of this H in G. So, that is going to be exactly G mod H. So, because this G mod H is a orbit, so this is going to be G invariant subset of sigma. So, this is sitting inside sigma. But what is the property of this orbit? The property of the orbit is exactly the cardinality of the orbit is exactly the cardinality of G mod H, which is going to be m. Note that P does not divide m. So, that is the property. Okay. So, if you look at this orbit, you can see that P is not dividing the cardinality of this orbit. And another thing you can easily check, if you look at this stabilizer of H, okay, the stabilizer of this H inside G, okay. So, this is something we have worked out already. This is going to be those G in G such that GH is going to be H, okay. But H is being a subgroup will imply that this GH is going to be exactly H. So, H can be realized as stabilizer of this H, okay, under this action. So, this sigma, this G acts on this sigma, and then this H is being a subgroup of G such that the H having cardinality p power k makes it H belongs to the sigma. If you look at the stabilizer of this H, you get back H. So, this motivates us to look for this particular action and then look for some orbit satisfying this property, okay. So, that is that P does not divide, P does not divide the orbit of the cardinality of the orbit. So, then look at the fix some element in that orbit and then look at stabilizer of that orbit, okay. So, we expect that should do the work, okay. So, let us try to prove, okay, here is the proof. So, the proof starts here, okay, the real proof. So, see that G acts on sigma, S is subset of G having exactly cardinality p power k. So, then what is the cardinality of sigma? Cardinality of sigma is going to be you are choosing all possible subsets of G that are having p power k elements. What is the cardinality of G? Cardinality of G is p power k times m. So, it is going to be exactly p power k times m choose p power k. So, this is going to be the cardinality of sigma. So, you have this natural action of G on this sigma given by G dot S equal to G S, the left multiplication. This is the action. Okay. So, now what we want to do, you know that the sigma can be actually partitioned into orbits. Okay. You can write this sigma as disjoint union of orbits, disjoint union of orbits. Okay. Now, using this orbit decomposition, you can see that sigma can be written as the cardinality of sigma is summation the cardinality of all the orbits, where orbits runs over some, let us say 1 to r. There are r orbits. Okay. So, now you can see that this p power k, m choose p power k. So, this is indeed congruent to m modulo p. Okay. So, this I will check later. Okay. So, this is a fact, we will verify in a minute. Okay. The fact actually states p power k m choose p power k. So, if you take this number is exactly congruent to m modulo p. Okay. So, in particularly p does not divide the left hand side, p power k m choose p power k. So, p does not divide the cardinality of sigma. Okay. So, this immediately implies this, because m is relatively prime, as m is relatively prime with p. If p divides this cardinality of sigma, then m is congruent to 0 modulo p, that is absurd. So, since p does not divide this cardinality of sigma, so that would imply immediately p does not divide the cardinality of sigma, there exists I such that p does not divide one of the orbit, cardinality of the one of the orbit. Okay. So, fix such orbit, call it O, okay, and then choose some element, S in that O. Okay. You just fix some element here. So, in particularly O becomes OS. Okay. So, now you take this GS, which is the stabilizer of this S inside G. So, this is going to be a subgroup inside G. Okay. So, this is our subgroup. Okay. So, now we want to claim that this is the subgroup that we wanted. Okay. The group that we have here is going to be exactly having p power k elements. So, let us try to verify that. Okay. So, this is our silo p subgroup, that is our claim. So, let us look at what is the cardinality of this. Okay. The cardinality of OS is going to be cardinality of G divided by cardinality of GS. So, this is by orbit stabilizer theorem. Okay. This is by orbit stabilizer theorem. Okay. So, now if you look at this equation, you can see that p power k times m is exactly equal to cardinality of OS times cardinality of GS. But what we have, p does not divide the cardinality of OS. That means whatever power you have here, that should be dividing this cardinality of GS. Okay. So, this immediately implies p power k divides the cardinality of GS. So, that immediately implies that p power k is less than or equal to the cardinality of GS. Okay. So, the cardinality of this stabilizer is indeed having at least p power k elements, because p does not divide this cardinality of the orbit. Okay. So, we wanted to prove that this stabilizer actually having exactly p power k elements. We proved one way. and we want to really compute what happens to the stabilizer. Okay, let us call this as H, okay, just to simplify the notation. So, recall this is exactly those G in G such that it fixes this capital S. Capital S is a set, capital S is a set that having exactly p power k elements. Okay. So, this S is just a subset of G. So, this is just a subset. But since this H actually leaves this S invariant, okay, this equation actually tells, okay, whenever you take some element x in capital S, G in H, then G x is in S. That means we have this following action. So, H naturally acts on capital S via this left multiplication again. So, you take H and then you take x, okay. So, and then you say that H dot x is just H x. So, this is for H in H and x in capital S. So, now this gives you new action of H on S. Okay. This is, since again left multiplication, it is easy to verify this is an action. So, now H is acting on S, okay. In particularly if you take some S naught inside S, look at the orbit, okay, inside this H. What is this? This is those H dot S naught where H in capital H. Okay. So, you can see that this orbit with respect to this action is going to be H S naught H in H. So, this is a subset of S, that is all we know. So, now again use orbit stabilizer theorem, okay, one more time you use. So, the cardinality of this orbit now computed using orbit stabilizer theorem. So, this is going to be exactly equal to the cardinality of H divided by the cardinality of H S naught. What is H S naught? It is those elements of H that fixes S naught. Okay. So, this is what this, but this is going to be less than or equal to the cardinality of S, which is p power k. So, let us compute what is H S naught. H S naught is going to be those H in H. So, because this is stabilizer of S naught in H. Okay. So, this is the stabilizer of S naught in H. So, this is those H in H such that H S naught equal to S naught. But H S naught is just left multiplication. We are in the group only. We are in the group G. H S naught equal to S naught is going to give you, by cancelling S naught, H equal to identity. So, this, that means this is exactly is identity. So, that means the orbit is exactly H, the cardinality of the orbit is exactly the cardinality of H, which is less than or equal to p power k. But if you go back, we already have one other inequality. So, this is the cardinality of H. Okay. So, we already have p power k is less than or equal to cardinality of H, and here we are saying that the cardinality of H is less than or equal to p power k. So, that proves H is having exactly cardinality p power k. So, since H is realized as stabilizer of something, so it must be a subgroup. So, H is a subgroup. So, that is already we have. So, that means in from this proof we can see that, so by acting G naturally on this set of all subsets of G that are having p power k and choosing the orbit properly. So, choose the orbit such that this p does not divide the orbit. From that we actually got this subgroup which has exactly cardinality p power k. So, the upshot, okay, let me write it here. So, make G act on this sigma, which is those subsets of G such that the cardinality of S is p power k. So, then look at choose orbit of sigma, okay, orbit of course with respect to this action such that p does not divide the cardinality of the orbit. Then choose S is in this orbit, look at this G S which is the stabilizer of this particular S inside this group G. Then this is a subgroup of G. We proved that the cardinality of GS is exactly P power K, and in particularly GS is a silo P subgroup of G. Okay. So, this is what we have proved. So, let us look at this very closely, and then we try to understand what happens to the orbit. But before that we still need to check this fact. Okay. This is something we assumed. So, if you take this number p power k times m choose p power k. So, that must be congruent to m modulo p. So, let us see how one can prove this. So, this is basically doing arithmetic modulo p, and we have to do it using the polynomials. Okay. So, let us recall 1 plus x power n is nothing but what, using the binomial expansion you can see that this is exactly equal to n choose r x power r varies from 0 to n. So, this is just binomial expansion. So, where n choose r is nothing but n factorial divided by r factorial n minus r factorial. So, now let us compute what happens to n plus x power p power k times m. Okay. So, if you do this modulo p, this is going to be exactly equal to okay, 1 plus x power p power k power m modulo p, okay, or inside z modulo gp pz. So, this is something I will leave it to you to verify. Okay. So, modulo this thing. So, what it says that when you raise it power p power k. Okay. So, basically this follows from the following fact. If you take a plus b power p. So, if you go modulo p, then it is going to be a power p plus b power p modulo prime p. Okay. So, this is something you can verify, and from this you can conclude this. You raise it power again and again, you see that you get this. Okay. And this is again just comes from the binomial expansion, because every time you will be having p choose r when r is actually not equal to 0 and not equal to p, you will be having exactly p divides this p choose r. So, this just uses p divides p choose r for r not equal to 0 and p. So, now if you raise it power again a plus b power p square, okay, this is going to be a power p plus b power p power p. So, this is concurrent to this modulo p. So, then you can see that this will become again concurrent to a power p square plus b power p square modulo p. Okay. So, from this you get this, and then by induction you can prove that 1 plus x power p power k times m is congruent to 1 plus x power p power k power m modulo p. Now, again use binomial expansion, then you can see that the coefficient of this p power k m. Okay. So, in this polynomial, so in 1 plus x power 1 plus x power p power k power m, in this polynomial the coefficient of x power p power k times m is exactly m. Okay. So, that means you can see that. So, but on the left side here, so the coefficient, same coefficient is going to be, we are going to calculate the coefficient wise. The coefficient of p power k x power p power k m in 1 plus x power p power k times m. Okay, we want to sorry, we will calculate the coefficient of x power p power k only, not p power k. So, this is just x power p power k, and here also it is going to be x power p power k. So, the coefficient of x power p power k in 1 plus x power p power k times m, this is exactly equal to p power k m choose p power k. So, this is going to be exactly congruent to m modulo p, because this is the coefficient here on the right side here. Okay, that is what we have proved. So, that proves that this p power k m choose p power k is actually indeed congruent to m modulo p. Okay, this is verified. So, that actually completes the proof of first Sylow's theorem. So, let us make one small observation and then stop. Okay. So, if we take this orbit that we have chosen, okay, let us see like what can we say more about that orbit. So, if you recall, the sigma is written as union of orbits, and then we have chosen O, which is an orbit, such that this p does not divide the cardinality of the orbit. So, then we have chosen S from the orbit, and then we immediately observe that O equal to OS, and our H is nothing but the stabilizer. Okay. So, now if you take some other t inside your orbit, okay, so let some other t, then let us see what happens to this. Okay. So, you can see that this t is going to be some gs for some g in capital G. Okay. So, then we are going to say that, so from our proof we already seen that, so this H acts on this capital S, and if you fix some S naught in capital S, then we saw that this HS naught is going to be identity, and this OS naught H is naturally has bijective correspondent with H. In particularly, this OS naught H is going to be S. So, we have a natural map from H to this S given by H goes to HS naught. So, that means this S can be identified with HS naught. Okay. This is actually very clear from our proof, because you look at this action of H on this capital S. So, this is what we get from the proof. So, in particularly we want to compare what happens to some other element t in O. Okay. So, t will be just a GS. So, now if you do some computation, then you can see that, so this t is going to be exactly equal to G H S naught, which is exactly G S naught inverse. Okay. Maybe you can write it like this, S naught inverse H S naught. So, that means if you take this element to be some A, so then the t can be identified as A times some k, where k is just the conjugate of this H. Okay. So, in particularly what we have seen, so any element t of this orbit O can be realized as is equal to left coset of this k, left coset of this k, where k is given by this specific group S naught inverse H S naught. Note that this S naught is already fixed, that is coming from this capital S. Okay. And k is a subgroup of G, that is obvious because it is a conjugate of H. So, that means what it says, okay, I will leave it to verify. Okay, this is already there in the proof. This O can be identified as, okay, so this is exactly equal to G modulo k. So, it is not just some orbit, it is indeed the orbit that naturally comes from some subgroup. Okay. So, because that is what our motivation said. Na? So, if we start with group H having this property, then we saw that this G mod H can be realized as the orbit. Okay. So, that is what here also we are saying. So, note that the cardinality of K is same as cardinality of H, which is exactly P power K. So, in particularly the cardinality of the orbit is going to be cardinality of G divided by the cardinality of K, which is going to be M. So, the orbit that we have chosen such a way that P does not divide the cardinality of the orbit forces that the cardinality of the orbit must be equal to M. So, this is all inbuilt in the construction. Okay. It is not some random orbit, it is just orbit that is having exactly m number of elements, and this orbit also comes from the left coset of some silo P subgroup. Of course, now we have chosen some different silo P subgroup which is conjugate of H. Okay. So, that is the observation that we are making. It is not some the way that we have chosen seems to be somewhat arbitrary, but this P does not divide the orbit of this the cardinality of the orbit forces that this orbit is nothing but G mod K for some K silo P subgroup. So, this is very important observation, this will be used later. Okay, I will stop here and I will actually continue with the proof of second and the third Sylow's theorem in the next class. Thank you.